Soil erosion is defined as the wearing away of soil by water, wind, and other natural forces, and is deemed a major ecological problem. This is due to the heavy rainfall that may occur in certain areas, causing the nutrient-rich topsoil to disappear and be washed away. As a result of this, waterways often end up polluted with extreme amounts of pesticides and fertilizers. Not only does soil erosion take a massive toll on productive farmlands, however, it can also jeopardize human life and property by causing mud and landslides. It is estimated that the economic cost of soil erosion is $400 billion, and thus it is evident that this is a serious problem. With this in mind, it is important to note that there is a simple solution. Soil erosion occurs when soil is saturated from excess amounts of rain, and therefore plants are unable to absorb any more water. This water is called runoff and flows directly over the soil's surface as there is nowhere else for it to go. The solution to combat this problem is to use plants that have extensive root systems to essentially latch on to the soil and keep it intact. Plants help to absorb water in soil, and as a result of this, it makes it more difficult for water to wash soil away. Plants not only help reduce the effects of erosion, but also in other ways, such as breaking wind barriers that may contribute to blowing dry topsoil away. After building a firm knowledge base about soil erosion and the ways in which this problem can be solved, a group experiment was conducted. The investigation was based upon the theory that the amount of soil erosion would be greatly affected by the type of plants planted, as well as its root systems after surviving a heavy downpour of rain. As a group, it was predicted that the bread pan containing only soil would produce more soil erosion than the bread pans with plants in them. The thinking behind this conclusion was purely based upon the growth of the different root systems of each plant and their ability to latch on to the surrounding soil. While conducting this investigation, fair testing was used. Fair testing is defined as changing one factor at a time while keeping all of the other conditions within the experiment the same. Essentially, one variable must be changed, one must be measured, and the final one must remain the same. It is imperative that when conducting any experiment, fair testing is used in order to record the most accurate results possible. In relation to the soil erosion investigation, as a group it was decided that the variable that would be changed was the type of plants used. A variety of plants were chosen according to their root systems, due to the fact that a realistic and real-world replication of a soil erosion situation wanted to be achieved. The variable that was measured was the amount of soil that was washed away from each bread pan after mimicking a heavy downpour of rain. The factors that remain the same were the amount of water and the pouring mechanism used, as well as the type and amount of soil put in each bread pan. By carefully monitoring each variable during the experiment, it was evident in the results recorded that a fair test had been conducted. The equipment required for the fair test included 5 small bread pans to plant the different seed or seedlings in. 3 large empty pans were used for the drainage and erosion during the experiment. A variety of seed or seedlings were needed. For the purpose of this experiment, we used radish seeds, zucchini seedlings, and chili seedlings. Soil was used to plant the seeds. We used a quarter of a 25-litre bag and a spade to pack the soil firmly. Skewers were used to hold up the zucchini plants as they were quite flimsy. This ensured that the plant's growth was maximised. Zip ties were then used to secure the skewers to the plants to act as a wall for the plant to lean on. A screwdriver to poke holes in the bread tin for drainage was also required, as well as a watering can to water the plants with. Kitchen scales were used to weigh the eroded soil during the fair test. Lastly, a results table was constructed to record the data.
The first step in conducting the fair test involved filling 4 bread pans with soil, leaving enough space at the top to ensure the pan doesn't overflow when the plants were added. The seeds were then planted in the bread pans. We planted the seeds quite close together, more than what the packet instructed. This enabled us to see clearer root systems in the soil of the plants, which facilitated more effective results. We placed a sticky note on each pan so that we could clearly identify what seeds were in each pan and what number trial they were. Following this, a screwdriver was used to puncture holes along the bottom edge of the pans to simulate drainage. This allowed excess water to drain out of the pans and prevented us from overwatering the plants. The plants were placed outdoors where direct sunlight was accessible. The plants were watered once a day over a 2-week period. This simulated a real-life rainfall application, which gave the plants time to grow and form strong root systems before the fair test was conducted. It was important to ensure that all plants were watered with the same amount of water each time to make the experiment a fair test. This also minimized the chances of flooding or overwatering. To conduct the fair test, we began by using a set of kitchen scales to weigh the empty bread pans. We recorded these results to help calculate the amount of soil erosion produced in each bread pan after watering. Next, 2 vertical cuts were created halfway down the short side of each bread pan like so. This allowed us to fold down one side of the pan to expose the soil. The open side of the bread pans were placed into the larger bread pans with the opposite side propped up to replicate a hill. You can use a container for this. A watering can was then used to water each plant and replicate rainfall. It is important to make sure that the same amount of water is used to water the plant each time. To achieve this, we filled a small jug with the same amount of water for each trial, before pouring it into the watering can. This ensured that the total amount of water received by each plant is equal, allowing for accurate results. Another aspect that contributed to the fair test was the position of the watering can when watering the bread pans. The watering can was held up at the same height each time, high enough to ensure the water lands directly on the entire pan at once. This simulates even rainfall across the entire area. Furthermore, the amount of time the plants were watered for was also considered to ensure each trial was equally tested. We completed this by counting to 5 each time.
Mississippi 2, Mississippi 3, Mississippi 4, Mississippi 5, Mississippi.
After the plants were watered, they were removed from the larger bread pan and the excess water was drained. This left the eroded soil in the larger bread pan. The kitchen scales were then used to measure the mass of eroded soil in the pan. To calculate the amount of soil each trial produced, the mass of the bread pan after the soil eroded was taken away from the mass measurement of the empty bread pan. As depicted on the screen, this data was entered into the results table and another 2 trials were carried out to get an average reading of soil erosion for each plant. The data collected from the experiment is an example of primary data. Primary data is defined as the collection of original data which is gathered by the researcher. In this experiment, that was us. Primary data is often taken after the researcher has developed insight into an investigation or inquiry through reviewing secondary research. As depicted on the screen, the table presents primary data collected from the FAIR test. A bar graph has been constructed using the results from the investigation to depict a visual representation, which is evident on the screen.
To understand why plants and seeds react differently when watered, we had to investigate each plant's root system. All plants have a root system. They are unseen and buried beneath the soil. Plant roots perform functions that are necessary to a plant's life. The roots collect water and nutrients for the plant and secure it to the soil. There are 2 basic types of root systems. One type is taproot, which grows vertically and has lateral branches. The other type has fibrous branching roots that make a network close to the soil surface. Some plants have either a taproot or fibrous roots, and some plants combine the 2 systems. All seeds and plants used in the FAIR test have a taproot root system. The growth and positioning of the lateral branch roots determine the strength of the root system. The strength of the root system ultimately affects the amount of soil erosion produced by the plant. The data collected from the FAIR test indicates that plants do have the ability to stop or reduce soil erosion. It is evident that the different variables used in the FAIR test have diverse outcomes. As depicted in the data collection table, the zucchini plant eroded 6.13 grams on average of soil when watered. This was the smallest amount of soil produced throughout the entire duration of the FAIR test. In comparison, the bread pan with no seeds produced a gigantic 19.1 grams on average of soil when watered. Consequently, our prediction of the FAIR test was supported, and it is evident that plants containing stronger root systems produce less soil erosion. Furthermore, the radish and chili seedlings produced approximately 12 grams of soil on average when watered. The soil evident at the end of these two trials was greater than the soil that eroded from the zucchini plants, however was less than the soil produced from the plantless bread pans. This is because the radish and chili seeds had formed weaker root systems, allowing the lateral branches to latch onto a minimal amount of surrounding soil, in comparison to the plantless bread pans which had no root system for the soil to cling onto. Before conducting the FAIR test, we cut open one side of each plant's bread pan to conduct visual observations of the root systems. The root system of the zucchini was dense. The soil was very firm and it clung to the roots of the plant. When the plant was watered, the roots absorbed the water and held the soil in place. The strong root system therefore makes it harder for the water to wash the soil away and limits erosion. In comparison, a visual inspection of the chili plants showed a shallow root system. Consequently, when the chili seeds were watered, the water struggled to stick to the soil and roots. The less dense root system resulted in an increase in the amount of soil erosion. Research has shown that the organic soil is beneficial for chili plants as it keeps the soil damper for longer periods of time. The content covered in this research investigation aligns with the Year 4 content descriptor, Changes in the Earth's Surface. This is found in the science strand of the Australian curriculum. An investigation requires students to conduct a FAIR test and provides both visual and hands-on experiences. In a classroom environment, the students would plant the seeds, water them, and record data about their growth on a weekly basis to develop additional science concepts. When conducting the FAIR test, the teacher would set the plants up at the front of the classroom so all students could visually see. First, the teacher would demonstrate how to correctly water the plants and record the soil erosion data. After this demonstration, the students might water the remaining seeds in small groups. To conclude the lesson, the teacher might facilitate a discussion on the results from the FAIR test. In addition, a research-based project could be given to students to learn about plant root systems prior to the FAIR test so that students can develop a basic understanding of these science concepts before participating in the experiment. Students could draw diagrams with labels of the root systems. As an extension activity, the teacher could then ask students to construct their own FAIR test with their new learnt knowledge using the same science concepts. The core science concepts taught within the inquiry project focus on building students' knowledge about the causes of soil erosion. Information regarding different plant root systems, including both taproot and fibrous, are explored. Students are also exposed to real-world applications throughout the investigation. These include the impacts and costs of soil erosion on our Earth, as well as methods to prevent soil erosion. Key vocabulary such as soil erosion, runoff, saturated, and economic botany are heavily embedded into the research investigation. Students have multiple misconceptions about soil erosion. Some students think that soil erosion is the process by which weathered particles are deposited into a new location. They also think that soil erosion happens quickly and is always bad. Overall, this science inquiry investigation is an engaging way to teach primary school students real-world science concepts such as the erosion of soil.